photodynamic therapy is a non-invasive medical technique that uses the combination of a photosensitizer and a light source in order to generate singlet oxygen and other reactive oxygen species that leads to cell death, showing a way out of the adverse effects of conventional therapies. For this, ruthenium-2 complexes show many attractive properties for PDT applications, including strong absorption throughout the visible range, intense emission with long-lived triplet excited state, besides chemical and photochemical stability. We choose to work with these complexes, and in order to modify their properties, we add it to a ruthenium-3 phenanthrene, a derivatized phenanthrene ligand with a perilene diimide ring, organic dye with a high molar extinction coefficient in the visible region, high fluorescence quantum yield, photochemical stability, and excellent electron acceptorability. The coordination of the P-expensive ligand perilene diimide resulted in a significant improvement in optical properties of the dyed ruthenium perilene. For example, the absorption spectrum is characterized as the sum of the perilene and Hu-3 phenanthrene spectra, and even after coordination the individual characteristics of each core have been preserved. The excitation at the ruthenium core produced an emission referring to the MLCT deactivation. In contrast, when excited at the perilene core, the emission from the internal transitions of the perilene ligand was observed. The coordination also allowed an efficient and long-lived PDI triplet generation, with lifetime of 1.8 microsecond can sensitize molecular oxygen to yield singlet oxygen, with efficiencies of generation as high as 0.57. And with that in mind, the objective of the work is to evaluate the efficiency of the complex in antimicrobial photodynamic therapy against Spodotrix brasiliensis and Candida albicans, and the efficiency in photodynamic therapy against B16F10 murine melanoma cancer cells. For photodynamic inactivation tests, the incubation time was defined using fluorescence confocal microscopy, and the best drug light interval was 20 minutes, when our photosensitizer remains adhered to the microorganism. So the fungi were incubated for 20 minutes with the complex and brought to irradiation, using dose of 36 joules in 450 nanometers and a dose of 25.2 joules when irradiated in 525 nanometers. Colonies were counted and compared to the control groups. And for Spodotrix brasiliensis, our photosensitizer showed a reduction of 2 logs in concentrations higher than 5 micromolar in the dark. Besides the cytotoxic effect in the dark, with blue light treatment showed a total reduction of the colonies with 5 micromolar of the ruthenium-2 complex, and with green light treatment only 0.5 micromolar was needed to completely reduce the colonies of Spodotrix. Using the same light doses, the tests in Candida albicans showed that this complex completely reduced the colonies of the fungus with 0.5 micromolar when treated with the blue light. In contrast, with the green light treatment, only 0.05 micromolar of the ruthenium-2 photosensitizer was needed. For PDT tests, the viability of B16F10 murine melanoma cell line in the dark and under irradiation were evaluated using the MTT-assay, and the application of this complex in PDT in vitro experiments showed no significant effect on cell viability or changes in cell morphology after 24 hours of incubation in the dark. However, under blue light treatment at the 420 nanometers using a dose of 0.58 joules, the complex exhibits a strong photocytotoxic effect, displaying IC50 values of 0.5 micromolar. And under green light treatment at the 518 nanometers using a dose of 0.41 joules, the complex exhibits IC50 values of 1.2 micromolar. This work concludes that the complex proved to be an excellent photosensitizer in photodynamic therapy and antimicrobial photodynamic therapy. In addition to acting better in low-energy regions, it proves to be useful in terms of fungal infections and skin cancer treatment. Thank you.